The world is abuzz with big data. I've been talking about it for the last 10 years now. There being a lot of data. Well, big data makes big problems seem bigger. Big data makes big problems in some ways. So oftentimes people seek to make big data more manageable before they can proceed ahead. The topic we're going to look at here today is designed to make big data to be more manageable by shrinking it into a fewer number of dimensions or factors. So let's get started. We're going to examine here the topic of dimension reduction using two techniques called factor analysis and principal components analysis. I'll refer to the latter as PCA. We're going to examine the motivation for this technique, examine the methods, conduct PCA, and then briefly conduct factor analysis also. Dimension reduction is a class of procedures for reducing big data, reducing a large amount of data. It does so by representing variables in a data set using a fewer number of factors or components. The natural question is, why even bother? Well, we want to reduce our dimensions or variables to a fewer number of dimensions because our variables may have a common underlying theme to them. There may be something linking them together based on their meaning. Imagine a survey questionnaire where people are asked for 4 or 5 questions about pretty much the same issue, like about satisfaction. There may be satisfaction about different aspects of the experience, but they're really about satisfaction. They might fit nicely into a theme of satisfaction with the service. Similarly, there may be a couple of questions asked in the survey that get at somebody's likelihood to share the experience with other friends. There may be an item asking them to share the experience with their friends, share the experience with their family, and so on. And these questions might fit into a group or a block or a construct of intention to spread word of mouth. So if your variables have a common meaning to them, semantically they're similar, then you may want to group them into a construct. Variables may also be similar because of some statistical similarity. Mathematically or statistically, they may be correlated and therefore similar in that sense. Furthermore, if you have a lot of data, reducing that to a fewer number dimension helps tell a more lucid story. It makes it easier to interpret and to communicate with stakeholders. These are all very good reasons why one wants to reduce a large number of variables to a fewer number of dimensions. Furthermore, if you're engaging in predictive modeling, having too many variables is also termed as the curse of dimensionality. You've got way more features than you can reasonably handle. And this may cause associated problems in predictive modeling like model overfitting, which is where your model works really well on the trained sample, but doesn't generalize to other samples. Or it might result in high levels of multicollinearity, which may lead to very aberrant inferences. Lastly, if you've got too many variables in your data set, more so than your number of observations, it may not even be possible to conduct certain predictive modeling techniques like linear regression. Here are some research questions that dimension reduction might address. If you have X number of items in a survey, let's say 24, and you want to represent them using a fewer number of constructs, you could use dimension reduction. You've got a large number of variables, you want to shrink that to a fewer number of factors components, again, that are, again, semantically meaningful, you could use dimension reduction. In general, if you've got a really large data set, large by way of number of variables, then you can shrink that into a fewer number of factors or components. This technique is conducted using, or this method is conducted using techniques such as PCA, factor analysis, singular value decomposition, and so on. Dimension reduction is an interdependence technique, which means it is designed to look at interrelationships amongst the variables, hence also termed as an unsupervised learning technique. The data doesn't have labels to them. There's an explicit distinction of which are independent variables and which is the dependent variable. We're merely looking at connections or linkages or associations amongst the various variables to find some sort of a structure. You can think of this as some sort of pattern analysis. Unlike regression-like techniques, there isn't one single perfect solution that the algorithm will converge at. Rather, you're going to get many good solutions from dimension reduction. And then one has to bring in domain knowledge to pick out which of these solutions is the desirable one. In some ways, dimension reduction is similar to clustering. This is because in both techniques, the goal is to group data together. The difference is in clustering, we group observations. In dimension reduction, we group variables. Now, getting a little off topic here, I find it helpful to think about two analogies that help understand the concept of dimension reduction. In the world of dimension reduction, there is some sort of grouping we do of variables. The question is, how do we group variables? To understand this process, imagine for a second you find yourself on a tropical island. You're taking a walk down a beach, and you have a bottle of water, and you decide to fill the bottle of water with whatever you could find on the beach. So there's some water in the bottle, you add some sand to it, shells, small pebbles, rocks, salt water, so on. You add all that to this bottle of water, okay? Put the cap back on, tight, and then imagine you attach a string to the end, and with this mixture of ingredients, including sand, water, mud, pebbles, shells, you spin the bottle rapidly. This is what happens in a centrifuge. You spin this rapidly, what's going to happen is, are you thinking of what's going to happen? Think about it. Maybe pause the video. As you spin this rapidly, what's going to happen is all the heavier particles, the rocks, will go to the bottom, and the particles that are lighter than the rocks, the smaller pebbles or smaller, lighter rocks, will be one level above that. And then you'd have sand above that, and then water on top. Fairly clear water on top. Okay. Factor analysis or dimension reduction is a bit like that. What we're going to do is we're going to spin the data rapidly, and what will happen is all the particles or objects that are similar will stick together. The small rocks will stick with other similar small rocks because they're somewhat similar in terms of their physical characteristics. Small pebbles will stick with small pebbles. Sand will stick with sand, forming a sand layer. And then the cool water molecules will stick with other cool water molecules, forming a layer of water. In a sense, then, you're getting a clear grouping or bands of data, well, sand, rock, so on. But again, they're sticking together based on some similarity. In the world of factor analysis or PCA, the stickiness is figured out by looking at correlation. Okay. Now, that was one analogy that we're talking about. Here's the second one. The second one it goes back to the early days of the web. As far back as 1995, when the web was commercialized, people dubbed www as being the worldwide, wait for it, wait. Because it took so long to download anything from the web, especially pictures would take forever to download. This was a time of 40.4 kbps dial-up modems. People figured, well, since while we wait for technology to catch up and bandwidth to grow, let's find a way to make the files themselves more compact and smaller to download. Well, making smaller files meant that you would, have the picture smaller. Somebody came up with the novel idea of coming up with a compression format for images, which took a long time to download. So what they did was they took a really complex looking file and shrunk it down to a smaller space. Let me give the intuition behind this using an example. Before I started this video, I went onto Google and I did a search for puppies. Here's what I came up with. And since I'm in video here, normally I would have asked you to pick a pup for me, but I made a choice here and picked a pup. And it's the guy I thought was the cutest of them all. So I picked this pup and I opened up the picture in another software called Paint, using Windows. So Paint it is. And here's what I got. So here's a picture. It looks like a solid picture. I want you to pay attention to the top, the title bar where it says the picture is a .jpg. That's the name of the file, the JPEG file. Okay, now all is good in the current resolution, current magnification at 50%. Let me, zoom in. Let's look into his eyes. It's a really cute pup. Let's zoom in more and really, really magnify and really peer into his eyes, maybe into his soul too. So as I zoom in and see what's happening to his eye, it's getting pretty, as my sons would put it, Minecraftish, or is it Lego-ish? It's getting very pixelated. Right? That solid eye earlier has gotten really pixelated. And it's not just about the eye, it's every part of the dog has gotten pixelated. The pup. Right? Look at his nose. Ooh, looks pretty scary. Okay, so the reason this happened is because what I'm showing you here is a JPEG file, which is a compression format for a bitmap file. This file has a size of, let's highlight this, 110 kilobytes. My guess is the original bitmap file this came from was probably about maybe 2 megabytes or maybe 4 megabytes. So you've gone from 2 or 4 megabytes down to 110 kilobytes. In doing so, some of the picture quality has been compromised. It's not as crisp as it was, in the original file. Dimension reduction is a bit like that. We're going to take a large amount of data, we're going to shrink it. In doing so, we're going to lose some information. So we'll lose some information quality. You might think, well, that's not a good thing. We're losing some information quality out there. It's not going to be as rich as before. But for all practical purposes, this pup looks just fine at 50% magnification, or even 100%. So that's a bit of what dimension reduction is we're going to shrink the data, and we're okay so long as information loss isn't too much. So we don't want to lose too much information. We want to preserve meaning and structure while only losing some information. That some information loss is sort of like a heuristic that we typically use of anywhere from, we say we want to make sure that we lose no more than 30%, at most maybe 40% you'd say. But so in other words, we want to preserve about at least, preferably 70%, but definitely more than 60% of the original information in our data when we conduct a PCA. Okay. So with those two analogies, hopefully I've conveyed to you the motivation and the thinking behind dimension reduction. In the next video, I'll go in and talk to you more about the how to conduct a PCA.